Dear student, in the last video we defined positive, negative and null sets and give some of its properties. In this video we discuss existence theorem for positive and negative set. So first we write down the statement of the theorem. Let x s mu be a sign measure space and E be a measurable subset of X such that measure of mu is positive and less than infinity, means finite, then there exists a positive set A of X such that A is contained in E and mu of A is greater than 0, less than infinity, means the measure of mu is a measure of A is also finite and positive. Okay, means A is proof. Okay, if E is itself a positive set, then we take A is equal to E. Okay, and hence the theorem follows. Next, if E is not a positive set, then there exists a measurable subset even of E and a least positive integer n1 such that mu of E1 is less than minus 1 upon n1. Okay, now if E minus E1 is a positive set, then we take A to be E minus E1. Okay, since E is written as E1 disjoint union A, this implies that mu of E is equal to mu of E1 plus mu of A, because mu is your sign measure and you know sign measure is finitely additive. Okay, so we write mu of A to be mu of E minus mu of E1, and this value is greater than 0 as mu of E is greater than 0 and mu of E1 is less than 0. Okay, so in that case the theorem follows. Okay, next, if E minus E1 is not a positive set, then there exists a measurable subset E2 of E minus E1 and a smallest positive integer n2 such that mu of e2 is less than minus 1 upon n2. Okay, what happened if e minus e1 disjoint union e2 is a positive set, then we take A is equal to E minus E1 disjoint union E2. Okay, since E is equal to E1 disjoint union E2 disjoint union A, this implies that mu of E is equal to mu of E1 plus mu of E2 plus mu of A. Over R, mu of A is equal to mu of E minus mu of E1 minus mu of E2, and this value is greater than 0 as mu of E is positive and mu of E1 less than 0, mu of E2 is also less than 0. Now we see that if E minus E1 union E2 is a positive set, then the theorem follows. Okay, and if E minus E1 union E2 is not a positive set, then we continuing in the similar manner, we can find pairwise disjoint finite number of measurable subsets E1, E2 and so on, En minus 1, and there is a least positive integer n2 nk and a measurable subset ek of E such that mu of ek is less than minus 1 upon nk. Okay, so if E minus union k is equal to 1 to n minus 1, ek is a positive set, then we take A is equal to E minus union k is equal to 1 to n minus 1 ek. Okay, since E is equal to union k is equal to 1 to n minus 1 ek disjoint union A, this implies that mu of E is equal to summation k is equal to 1 to n minus 1 mu of ek plus mu of A. Okay, now over R, mu of A is equal to mu of E minus summation k is equal to 1 to n minus 1 mu of ek. Okay, then this value is again greater than 0 because mu of E is greater than 0 and mu of ek is less than 0 for k less than or equal to n minus 1 and greater than or equal to 1. Okay, so in this case the result, the theorem follows. Okay, if E minus union k is equal to 1 to n minus 1 ek is not a positive set, then the process will not stopped. Okay, so we continue in the similar manner. We get a countable sequence of least positive integers nk, k is equal to 1 to infinity, and the corresponding pairwise disjoint sequence of measurable subsets ek, k is equal to 1 to infinity of E with mu of ek is less than minus 1 upon nk. Okay, so if E minus union k is equal to 1 to infinity ek is a positive set, then we take A to be E minus union k is equal to 1 to infinity ek. Okay, since E can be written as union k is equal to 1 to infinity ek union A, this implies that mu of E is equal to summation k is equal to 1 to infinity mu of ek plus mu of A, because you know that your signed measure is countably additive. Okay, so ORR we write mu of A to be mu of E minus summation k is equal to 1 to infinity mu of ek, and this can also be written as mu of A is equal to mu of E, sorry, not equal to, it is greater than, mu of A is greater than mu of E minus summation k is equal to 1 to infinity 1 upon nk. Okay, and now we assume this to be our equation star. Okay, since the right hand side of equation star the series summation k is equal to 1 to infinity 1 upon nk, or it is written as summation k is equal to 1 to infinity mu of ek, is absolutely convergent, because mu of e is finite. Okay, so mu of a is greater than 0, and hence theorem follows. Okay, if a is not a positive set, our aim is to prove a is a positive set. Okay, so let f be any measurable subset of a. Okay, that is, f is a subset of a. This implies that f is a subset of union k f is a subset of e minus union k is equal to 1 to infinity ek. Okay, so here this f is also contained in e minus union k is equal to 1 to n we write k k equal to 1 to n ek. Okay, so since f contains no measurable set with measure less than minus 1 upon nk minus 1, so obviously mu of f is greater than or equal to minus 1 upon nk minus 1. Okay, for sufficiently large nk. Okay, so mu of f is greater than or equal to 0 as nk tends to infinity. It means, this implies that what, our a is a positive set, and hence the theorem. This is the proof of existence theorem for positive set. And now we write down the statement of existence theorem for negative set. Let x s mu be a signed measure space and E be a measurable subset of x such that minus infinity less than mu of E less than 0, then there exists a negative set A of x such that A is contained in E and minus infinity is less than mu of A is less than 0. This theorem guarantees the existence of negative set. Okay, and the proof of this theorem is same as the proof of the above theorem by replacing the word positive by negative set. Okay, so I will stop here, and in the next video we prove Hahn decomposition theorem. Okay, bye bye.